All right, guys, welcome to CW Biohacks. We're talking about John McMurray's Organic Chemistry 10th edition textbook, and we're specifically going to focus on CWU Chem 361. So this is the first in a series of organic chemistry classes, and the goal of these videos are just to, boost my understanding of the material, and then hopefully whoever watches their understanding. So I'll be learning as much from your guys' comments as hopefully you will be from my commentary. So we're going to go chapter by chapter, every section of the chapter. So let's begin. So chapter 1, section 1. So in the beginning, there was the Word. And that Word had a C in it. And that C had 4 valence electrons. So organic chemistry is the study of carbon, and that's what we're going to be doing for this whole series. We're going to see carbon and see how it can create all sorts of molecules and bonds, and this molecule carbon is what is the basis of all of organic chemistry. So in the beginning, there was carbon, right? So now let's start talking. We got to start really basic. So this is some Gen Chem, review. So we have atoms, and atoms are positively charged nucleuses positively charged nucleus surrounded by negatively charged electrons. So this is everything that an atom is, and the nucleus of an atom is made of protons and neutrons. So protons are positive, and neutrons are neutral. They don't have any charge. So atoms are described by their atomic number. And the atomic number is just how many protons are in the atom. So let's take carbon, right? How many protons does carbon have? There's 6. And then the mass number, so carbon is 6, oxygen's 8, hydrogen's 1. So that's the atomic number. And then the mass number is the total number of protons and neutrons in the nucleus. Okay, so that's why carbon is 12, because there's an equal amount of protons and neutrons in the nucleus. So the atomic number for carbon is 6, and the mass number is 12. So all atoms of a specific element have the same atomic number. So I'll do an example, right? So carbon, there's a couple types of carbon, right? There's carbon 12, carbon 13, and carbon 14. So I'll write these down. So carbon 12, carbon 13, and carbon 14, okay? So what these are isotopes, okay? So isotopes are atoms with the same atomic number and a different mass number. Okay, so isotopes all have 6 protons, but they have a different number of neutrons. So these neutrally charged atoms in the nucleus, and that's what makes them isotopes. So again, isotopes are the same atomic number with a different mass number. And in nature, these carbon 12s are very common. 98%. Carbon 13s are 1.11%. And carbon 14s are negligible percentage. So most often we see are these carbon 12s, and these are isotopes, okay? And then we just got to go, one more thing is the weighted average of all the isotopes is called the atomic weight. So if we go to the atomic weight of carbon, it's about 12.011. So the weight of all these carbons put together is its atomic weight. Okay, so in 1.1, all we learn is that atoms are made of a positively charged nucleus surrounded by negatively charged electrons. And in the nucleus, there are protons and there are neutrons. And the protons are where you get the atomic number, and then the protons plus the neutrons are where you get the atomic mass. Okay, so now let's move on to 1.2. So surrounding this nucleus, this positively charged nucleus, we have orbitals, okay? And orbitals are different ways, and these orbitals are ways that the electrons organize themselves, okay? And there's 4 orbitals that we need to be familiar with, or the only 4 that I know of and that are talked about in the chemistry book, organic chemistry book. And those are the s orbital, the p orbital, the d orbital, and the f orbital, okay? And these orbitals go around the electrons, right? So if you know the periodic table, right, we have hydrogen, we have helium, we got these guys, then we got some here. Right up here, this is the 1s orbital. And then the 1s orbital includes hydrogen and helium. So this is the 1s1 and then the 1s2. And then we move down. And then down here, we got the 2s orbital. And then this 2s orbital, this is the 2s1, then we got 2s2. So the way we fill these orbitals is by the amount of energy, okay? So before we go into that, I'm just going to talk about the different shapes of the orbitals. So in the s orbital, it's spherical, s for spherical. So when we visualize it around the nucleus of the atom, it's a big circle, okay? So the s is spherical. Now the p orbital, and there's only one spot for electrons to go on the s orbital. On the p orbital, we call it dumbbell. That's how it orientates itself. And there's 3 spots where electrons can go on the p orbital. I'm sorry. And then the d orbital. So this is the p, and then the d orbital. We kind of think of it as a clover leaf. Okay, so we kind of think of it like this. The d orbital has 5 spots where it can take electrons, okay? So in the first order, so this is the first orbital. So now let's go back to our drawing now of our atom. So we have this positive nucleus, okay? Positive nucleus. And in our first orbital, this is the 1s, we have 2 electrons, okay? And then in the second orbital, we have the 1s, we have the 2s, so we have the 2s, but then we also have the 2p, that comes over here. So the second orbital can have 8 electrons because it has the 2 electrons from the 2s and 6 electrons from the 3p. So we can have this many. And this is not where the electrons go. I'm just putting them here for everyone's reference. Okay? So we have these orbitals. So in 1.2, we learn that surrounding the nucleus, we have these orbitals. Okay? And these orbitals are ways that the electrons organize themselves. Okay? And these orbitals, another word for them is shells. So we have the first shell, or maybe go back. We have the first shell and the second shell. And then we can have the third shell and the fourth shell and so forth. So now let's move on. So now in 1.3. So in 1.3, we're going to talk about electron configuration, okay? So we have the atom. We're back at the atom and it's positively charged. And we want to understand how the electrons configure themselves around the atom. And the way we do that is by the ground state electron configuration. Okay? And the ground state electron configuration has a pattern, right? So let's go back to our periodic table, right? So we got hydrogen, we got helium, and then we got lithium, and we got beryllium. And then I'll just draw these guys just for example. And we got boron and carbon and nitrogen and oxygen and fluorine and neon, okay? So these are the first 2 rows of the periodic table. So this is the 1s, right? So we got our atoms. So 1s. So 1s1, 1s2. So these are the first 2. And then we go down a row. Now we add a shell. We got our 2s1, 2s2. Bang. And now we keep going. Now we're on to the P's. Now we have our 2P. 2P's. And the P's, remember, have 6 spaces for the electrons to go in. So let's say if we're thinking about neon, it's going to have 1, 2, 3, 4, 5, 6. So it's going to have a full octet. All right. And a way we can visualize this very easily is writing out the electron configuration like so. So let's go 1s, 2s, 2p, and then we can go 3s, 3p, 3d, and then 4s, 4p, 4d, and then 4f. And we just keep on doing this. So we can go 5s, 5p, 5d, 5f. Okay? So we can write it like this. And there's a couple rules that we need to know when we're filling up our orbitals, okay? Because they don't fill up randomly. They're predictable, and there are rules that tell us what to do. So the first one is the Aufbau. I don't know if I'm pronouncing that right. Aufbau principle. And what this basically says is rule 1: the lowest energy orbitals fill up first. So you got to fill up 1s before you can fill up 2s. So we always got to start at 1s. So let's take boron, for example. Boron's configuration is 1s2, 2s2, 2p1. So we have to start with the 1s. We can't start with the 2s. We can't just jump ship. We got to start with the lowest orbital. Because if you think about their energy, it's kind of like this. So we got our orbital, that our 2s, and then our 2p, right? So we always got to start low to high and work our way up. The next one is only 2 electrons can occupy an orbital. So our second rule, only 2 electrons can occupy an orbital. And they must have an opposite spin. So you see how we have our electrons here. They're not both facing up. They gotta face the other way. And this is for the stability of the atom. If you got a bunch of electrons going in one direction, the atom's gonna be way less stable. I don't even know if that's possible. So for each of our orbitals, for each of the parts of the orbitals, the electrons can only fill up 1. Okay, and this is called the Pauli exclusion principle. So right now we have to start at the beginning, and we have to start at the beginning, and then each individual kind of space for the electron can only take 2 electrons, and they got to be opposite. All right, and now lastly, the third rule. This rule states, the third rule is that each orbital, you must fill in each orbital with 1 electron before you can go to the next, right? So let's take nitrogen for an example. So nitrogen's configuration is 1s2, 2s2, and then 2p3. Okay? So some people might draw it like this. No, that's incorrect. Are you kidding me? You got to fill them in. Like the third rule says, you got to fill in each orbital with 1 electron before moving to the next. So the correct way to do nitrogen is, so you got your 1s completely filled. You got your 2s completely filled. Okay, now you're going to 2p. So boom, boom, boom. That's how you do it, right? And then let's go to oxygen. So now let's say we're going to oxygen. So now we got sp4. What do? We got our 4. So now we can start moving. And now let's do fluorine. Fluorine, sp5. Boom. And now let's do neon. sp6. Bang. But see, I have to fill them all in with 1 before I can fill them with 2. Okay? So now, and let's relate this back to our our spins, right? Because it's important to keep relating things back to each other because these are going to become important in a second. So remember how the 1s is spherical? So we got the 1s around, so spherical, and then now we got the 2s, so now we got the second large orbital around the atom. And just keep this in mind, right? Keep in mind the shapes. So if we're talking about carbon, right? We have these p orbitals that are gonna be interacting with each other. So let's just keep that in the back of your mind because it's gonna become important here. So now let's move on to chapter 1.4. Okay, so in 1.3, so let's just keep referring back. So we have these atoms, and these atoms have electrons, and inside the atoms are positive protons, and on the outside we have negative electrons. Okay, and around these atoms, the way the electrons organize themselves went to orbitals, and we know that the orbitals are SPDF. That's how we've labeled them, and each layer has a different amount of spots, right? So S is 1, P has 3, D has 5, for instance. So now let's move on to 1.4. So now we're talking about the chemical bonding theory, okay? So let's go back to 1.1. So remember, in the beginning, there was the word, right? In the beginning, there was the word, and that word was carbon, okay? And carbon has 4 valence electrons, so 4 valence electrons. Okay, so what are valence electrons? Valence electrons are electrons that are on the outermost shell, and they have a special stability when it's full. So let's write that down. So the outermost shell is the valence shell. And the atoms on the outermost shell are called valence electrons. And these atoms want to have, it's called the rule of octets. These atoms want 8 valence electrons for the most part because that's when they feel stable. So if we go back to the periodic table, right, these atoms all the way on the right, they're what we call noble gases. So the noble gases, right? So we got helium, neon, argon, krypton, xenon, I think. Yeah, so we have these atoms right here, and these are the noble gases because they have 8 valence electrons. So they're full. They're not hungry for anything. You can't go shopping when you're hungry, and these guys don't even want to go shopping because they're not even hungry. They're so full of electrons. So if we think about the whole periodic table as like a big square, atoms for the most part want to reach the noble gases that are down here, the noble gases that are over here. And, atoms try to do that different ways. So like chlorine, for instance, will, take an electron, an ionic bond, and sodium, for instance, will give up an electron for it to become a cation. So there's different ways that these atoms, right? So like sodium can lose an electron, and like potassium can also lose an electron. These are like the alkali metals, for instance, or you can be a halogen like chlorine, fluorine, bromine, and iodine. These take electrons. Okay, so now let's get back to carbon, right? Because that's the word. So carbon is a non-metal, and carbon's really cool because it has 4 valence electrons, right? 4 valence electrons. So 4 valence electrons, okay? And carbon, it doesn't like to take or give, it likes to share. So carbon likes to share electrons. So carbon is really good at making all these bonds, right? So let's talk about a super simple atom, like the simplest one in organic chemistry. Let's talk about methane. So methane, CH4. And in methane, this carbon, it loves to share its electrons with all these hydrogens. So that's its way of reaching the octet, the 8. Because these hydrogens are coming in with 1 electron, and they share it because carbon already has 4, and they share, and they make a bond. And we can talk about that bond, and the way we just visualize it is in the line in this instance. So there's different ways that we can show these bonds, right? So when we go to methane, this is the Lewis structure. And the Lewis structure is just a way to visualize the bonds that are happening. So let's do this. So we got these electrons here. And what is going on here is one electron from the hydrogen is being shared with a carbon, and carbon's also sharing its electrons. So they're kind of, give and take a little bit. But carbon is more electronegative, so it wants more carbons. Hydrogens just want to give electrons. They're like, you get an electron, you get an electron, party time. And this is how we form a bond. When there's two electrons here, that's a bond. Let's try another atom. Let's try ammonia. So this is nitrogen. So NH3 is its formula. And the way we visualize it, hydrogens. So that's the way we do it. And remember, so these are bonds. So this is the hydrogen's giving a bond, and the nitrogen is more electronegative, so it wants that electron. So this is the Lewis structure. Another way to visualize it is the line bond structure. So now we're going to represent these bonds with just lines. So bang. What is this, John? Methane. And then what is this, John? Ammonia. So in this way, we're just visualizing these bonds. So that line there, all that means is bang, two electrons being shared. And you might be wondering, why are these hydrogens, why do they only need two electrons? Because I thought we were talking about the octet rule. So carbon wants 8 electrons. Why does hydrogen only want 2? Well, if we go back to the periodic table, right? You got hydrogen up here, and what is its closest noble gas? Helium. All right, so that's not how you write it. It's He, yeah. So for hydrogen, its closest noble gas is helium, right? And let's go think about carbon. Carbon's closest noble gas is neon. And now this is why the electron ground state configuration is important, because we're thinking, okay, why does hydrogen only want 1? Well, think about hydrogen here. It only has the 1s orbital, so it only needs 1 extra proton to become stable and become its closest noble gas, helium. But for carbon, its 1s is filled already, but it only has 4 electrons here, and its closest noble gas is neon, so it needs 4 more. So that's why hydrogen only needs 2. So you're going to see this one. So you're going to see hydrogen just, with a bond, and it's chilling. Whereas carbon and all these other non-metals that we're going to talk about, they need more. They need 4 bonds. So there's also valence electrons that are not bonding, okay? And we call these non-bonding electrons. Or lone pair electrons. Okay, so in these non-bonding, let's do H2O as an example. So these two electrons right here, these are called non-bonding electrons because they're not bonded to anything. So they're just kind of floating. And we'll talk about this in a second, but they're causing H2O to have a certain geometry. So just if you see in a line bond structure, you see 2 electrons floating out here. These are called non-bonding electrons. So now let's go to 1.5. So let's review again, right? So we started with carbon. It has 4 valence electrons, okay? And has an atomic number. And the atomic number is how many protons and how many neutrons. And now we know that the way these electrons, and it's this positive nucleus is surrounded by orbitals. And orbitals are just ways that electrons organize themselves, right? And these orbitals, we have a way to describe them, and that's called the ground state electron configuration. And we go from high to low. We fill 1 electron in each section before we go to the next. And we have to fill them with electrons with opposite rotation. And then, so now we have these electrons, and these molecules with the electrons, and they all want to be octets, and they all want to have 8 electrons. And the way they do that is by chemical bonding. And some of these examples, right, we have methane bonded with 4 hydrogens, and we have ammonia, nitrogen bonded with 3 electrons, right? So now we're going to go another way to describe it, or kind of further, let's keep furthering our understanding, is with the describing chemical bonds. And this is the valence bond theory. All right, so I'm going to give you guys a definition. So the valence bond theory is covalent bonds form when electron sharing occurs by overlap of 2 atomic orbitals. All right, so now let's do an example, right? So let's think about hydrogen. So we know that hydrogen, its ground state electron configuration is 1s, okay? Or 1s1, more specifically. So we got these hydrogens, right? So we have their 2 orbitals, and they have their electrons, right? Another way you can show that is like these. They have their orbitals, right? So they're both 1s. And we're going to form a covalent bond. And a covalent bond, so if we think about bond energy, so this is 1.5. And this kind of goes to like how much an electron wants to form bonds. And it's like electronegativity value and the difference between them. We can kind of describe it as like, so we can kind of go like this and then 2+. So if atoms aren't very polar to each other, right? So oxygen's all the way on the right of the periodic table. So it's pretty electronegative. And that also means, so it'll take electrons and that can make it polar. And by polar, what I mean is there's a lot of electrons on one side of the atom and not a lot on the other side. So like if we go back to water, this oxygen it wants the electrons more than the hydrogens. So the oxygen kind of takes on a slightly negative charge, and it's polar because it's pulling these hydrogens towards oxygen, okay? So now let's go back to here. So we have these hydrogens, and they're going to form a covalent bond, and they're not polar because they're both the same atom, so they both have the same electronegativity. So these are going to form together, and it's going to create H2, okay? And the reason why it creates H2 is because H2 has less energy than before. So H2 has less energy and is more stable. Like the rule of diffusion, high to low. Everything wants to go from high energy to low energy. Everything wants to go from the top of the building to the bottom of the building. That's just the way it just has to work. So these bonds make things make these molecules work together in a way where there's less energy. Okay? And another interesting thing is that these are forming a sigma bond. So a sigma bond. And these sigma bonds are head-to-head bonds, and we're going to learn a little bit more here in a second. And there's also another theory. So this is the valence theory, right? That they're sharing electrons, and they're sharing electrons by the overlap of 2 of their orbitals, okay? There's another theory that is mentioned in the textbook that I'll give the definition to, and it's called the orbital or molecular orbital theory. And we're going to reference it at the very end. I'll be honest, I'm not very familiar with this. I need to learn more about it. I think we're going to talk about more in my class. So that's what I mean. We're both learning from each other in this series. And what this says is covalent bonds form as a result of mathematical combinations of atomic orbitals. And this results in molecular orbitals. Lots of mispronunciation or misspelling there. But this is just another way. This is the truer way. It uses math. This is more of just a visual way, and it's going to do fine for what we need to happen, where you can just imagine these two orbitals of these atoms hit each other, and they form a bond. And then the molecular orbital theory is basically saying, well, we can describe this bond in numbers. So it's the more accurate way, but this way is a little bit easier to understand without a high math background. So now let's move on to 1.6. So 1.6 is talking about hybridization, specifically sp3 hybrid orbitals, and specifically the structure of methane. Okay, so let's go back to carbon. So carbon, we know, has 4 valence electrons. So we're going to put carbon. And we also know that carbon has one s orbital, because we know, so 2s. So let's think about the electron configuration. It goes 1s, then it goes 2s, and then it goes 2p, right? And we know that we have this many spots for each one. So carbon has this 1s orbital, but then also has these 3p orbitals, okay? And it can use these 3 orbitals to hybridize to form 4 equivalent atomic orbitals with a tetrahedral organization, okay? And the way this is going to look kind of in a visual sense is like this. So kind of visualize this black dot is carbon, and these are its orbitals, right? So these are the sp3 hybrids that surround the carbon. All right. So now let's kind of put something together. So let's think about methane, right? So let's think about carbon with these orbitals. So we got carbon here, and we need one for everybody. So we got these, and this one's gonna be kind of small. So carbon has all these orbitals, right? It has the 1s and 3p. So that's why there's 8 in total, because they kind of go off each other. And then we're going to combine it with 4 hydrogens. And remember, the hydrogens are just 1s, so they just have the spherical. And the way it's going to look, the way we can visualize it with this sp3 hybridization is like this. So we're just going to do this for like contrast. So here we have the carbon. It has the sp3. And these are the sp3. And remember, they're dumbbell. Okay? And then we have these spherical s orbitals from the hydrogen. So think of each of these circles as a hydrogen. And what this means, and this is the biggest thing, this hybridization is based mostly on the geometry. So we need to think about the way that these electrons, they push against each other. So let me draw another way of drawing methane. So in this formulation of methane, what's happening is that these 2 hydrogens are in line with the paper. This hydrogen is going behind the paper, and this hydrogen is coming at us, right? So it's kind of like sticking out in all directions. And the idea is that we want to form the most efficient bond angle between these hydrogens. And that bond angle is 109.5. Right, so these hydrogens, they want to be equally spread out around the orbital, and they want the most space that they can from each other. And this is the same as this. You know, what we're doing here is just visualizing it differently. So these are all those head-on bonds. So like this would be the equivalent of that. So all these bonds right here, I'll just draw another color, the equivalent of that. I know it's a little confusing. I was confused at first, and I don't even have the best way to explain it, but just kind of visualizing, right? Just remember that the P's are dumbbells. So the way we orientate them around the carbon, so around that middle carbon, is in a dumbbell configuration, Yeah. And then the H's are spherical, so we can kind of visualize them like this, like those spherical bonds. And then just imagine H's out here. And this is the same as this, but it's just a different way to draw it. Okay, and the reason why it kind of works like this with these bond angles, because it allows for the most efficient overlapping with other orbitals. And the reason, so this is the most efficient way carbon could organize the hydrogens, and then this is just another way to represent it visually. This is another way. So now let's keep going. Let's go to chapter 1, section 7. So let's talk about the sp3 hybrid orbitals and the structure of ethane. And here we're going to be talking a little bit about sigma bonds and pi bonds. Okay, so ethane. What ethane is a carbon bonded to another carbon. These hydrogens attached to it. And what's going on here is that ethane is forming a sigma bond right here. So ethane's forming a sigma bond between the carbons, and has a total of 7 sigma bonds. And a sigma bond is just a head-on-head, right? A sigma bond is the most efficient. It's a head-on-head bonding, and ethane's forming 7. Okay, so ethane's forming 7, and these are sp3 hybridized because everything is being bonded, right? The s orbital, right? Because the s orbital is being bonded, and all 3 p orbitals are being bonded. So this is going to be sp3 hybridized. And a way we can visualize that is like this. So we have our carbon, we got this sigma bond with another carbon, and then we have our p orbitals, and then this is the pi bond. So ethane has 1 pi bond, and a pi bond is just a side-to-side bond. So it has the sigma bond between. Oh, sorry, no, this is not ethane. This is ethylene. Ethylene is when we have the sigma bond. Yeah, because we wouldn't have a sigma bond for sp3. So these carbons, right? These carbons, since they have the p orbitals, for ethylene, it has sp2. I kind of jumped ahead, I'm sorry, to 1.8. So for the sp3, the easiest way I remember it is if a atom has 4 bonds, it is most likely sp3 hybridized. So if an atom has 4, it's sp3. If it has 3, it's sp2. If it has 2 bonds, it's sp. And all that's saying is that, so this carbon right here is bonded to 4 things. So that means that it's 2s and it's 2p are all filled one way or the other. So these guys are all filled one way or the other. So this means it's just sp3 hybridized. Whereas, if we go to ethylene, the formula is S2 and then HH. So if you go to ethylene, it's only bonded with 3 things. So even though it has a full octet, right, it has this double bond between the carbons, it's only bonded with 1, 2, 3 things. So its hybridization is going to be sp2. So these carbons here are going to be sp2 hybridized. And another way to visualize that, right, is that we have these hydrogens that are forming sigma bonds with the carbon. So sigma bonds with the carbon right here. And then these carbons are forming a sigma bond together. So we got 5 sigma bonds. But then these other p orbitals that aren't being affected, they're going to be forming a pi bond. And they're going to be forming 2 pi bonds. Because remember, it's a dumbbell. We have this dumbbell here, so it's above and below. And we have this above and below. And so this is 2 pi bonds right here. So pi bonds are side to side. And all this is saying is that 2p orbital is going to remain uncharged. Okay, so this one, it's a little confusing to wrap your mind around, even for me. But the best way to think about it is just sp3 equals 4 bonds with four separate atoms. sp2 is just 3 bonds with 3 separate atoms. 3 bonds with 3 atoms. And then sp is 2 bonds with 2 atoms. Because you can have multiple bonds, right? Because with this ethylene, you have a double bond with carbon, but it's still sp2 hybridized because it's only bonded with like 3 other atoms. Okay, so now we're still on 1.8. And yeah, so let's just talk about ethylene one last time. So when the carbon, when an sp2 carbon, so when a carbon that's bound to 2 hydrogen binds with another sp2 carbon, it forms a sigma bond, and that just means it's head to head. And it's the same thing here, head to head. And then it forms also 2 pi bonds. And it forms these 2 pi bonds between the unhybridized p orbitals, right? Because we have these s orbitals are filled right here. We got the s filled, and then we got these 2 p's, so the s is filled, and then the p right here and the p right here, but then we have this 1 p left, and that p needs to be filled, so it's going to form a pi bond with the other atom. Okay, and another kind of rule of thumb or trick, so if it's sp3, it's going to have 0 pi bonds because all the atoms are hybridized. If it's sp2, it's going to have 1 pi bond because 1 p orbital is unhybridized, and if it's just sp, it's going to have 2 pi bonds. I'm writing pi as if it's the food. 1 pi bond. So that's a good way to remember. So sp3 is 4 bonds, 0 pi bonds. sp2 is with 3 bonds with 3 different atoms. There's 1 pi bond, and sp2 or just sp is just bonded with 2 atoms, and there's 2 pi bonds. And like I said, the hybridization is all based on the geometry of the atom or the molecule. So in 1.10, we're talking about the hybridization of nitrogen, oxygen, phosphorus, and sulfur. So for ammonia, so like I said, this is just a rule of thumb because it's not always true, because ammonia is bonded with 3 atoms. So 3 atoms, you would think, oh, sp2, but no, because it has a lone pair. You got to remember, the lone pairs also play a role in the geometry. So this lone pair causes the angles right here to be around 107.1 degrees. And that's really similar if we go back up to our carbon. Oh, where did I write it? I think it's 109.5. Yeah, I'll find it. Yeah. But that 107 is really similar to the 109.5 of methane. So this is also considered sp3 hybridized. Same thing with oxygen, right? Oxygen, it's only bonded to two atoms, but because of these lone pairs, it kind of deviates from this rule of thumb that I use, and it's also sp3 hybridized because it's based on the geometry, because this angle is 105.5. Yeah, so and that's really close to 109.5. So that's why it's sp3 hybridized. So hybridization is based mostly on the geometry of the molecule, but this is a good trick that I've used, and I've gotten a lot of questions right just by using this trick, and it's really easy to remember. So now I'm gonna skip 1.11 that we haven't really spoken about that much in class, and it's just another way of I can just draw it here. It's just another way of visualizing how atoms bond and how they go from high energy to low energy. So if we have these carbons, right? We have these hydrogens. We have their 1s orbital filled. So this 1s1 for each. And then they go to H2 and they just fill this. And they just fill this, kind of plank. I don't know the exact term for it, but this ledge right here. And they have lower energy. I'm not really going to get into that because we haven't spoken about it much in class. So the last thing we're going to talk about is the skeletal structure. And this is like the big ticket item in organic chemistry because there's these molecules are so big that it's going to be hard to draw, with the Lewis structure. That takes a while. And then so does this, right? Both of those take a while. So there's a faster way to draw it, and that is the skeletal structure. So now we're going to be introducing the skeletal structure. And though there's 3 rules for the skeletal structure. So rule 1, carbon atoms are not usually shown. They are represented as lines. And they're assumed to be in each line. Assumed, right? 2, hydrogen bonded. Hydrogen's bonded to carbon. Isn't shown. So you just assume that each carbon has the maximum amount of nitrogens. So you just kind of fill that in with your mind. Now, last rule 3, atoms other than carbon and nitrogen are shown. So now let's see this in action, right? So let's think about ethane. We drew ethane. So ethane is this. So this is ethane, right? Carbon, single bond carbon, and 4 hydrogens bonded to it. So that took me about 5 to 10 seconds to draw. Boom. That's ethane in the skeletal structure. This is assumed to be a carbon. This is assumed to be a carbon. This is assumed to be the bond. And then we assume, because there's no charge, that it has the maximum amount of carbons. So we assume that there's 3 carbons on each side. Let's try propane. So propane, C3, H6. Yep. Or no, H8. I'm sorry, H8. Yeah. So that's propane. So we assume that there's 3, 3, 2. Okay? because these lines, so this is a carbon, this is a carbon, this is a carbon, and we assume that they have the maximum amount of hydrogens. So there's 3 here, 3 here. So 3, 3, and 2. Now let's try butane. So butane, C4H10, carbon, 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 carbon. So we got 4 carbons. And we got 3, 2, 2, 3. So that all around adds up to 10. Last one, let's try pentane. Pentane. 1, 2, 3, 4, 5 carbons. And then 3 hydrogens, 2, 2, 2, 3, 12. So this is the skeletal structure, and this is what we're going to get more into when we go to chapter 2 and 3. And it's just a way to very easily visualize. Let's do decane. Let me do decane. So that's C10. What would that be? H20, I believe. Or no, 22. Yep. C10H22. So I can go like this. That'll take me forever. End of the earth. There won't be any words left when that's done. Or I can do this. Oh, that was bad. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. 3, 2, 2, 2, 2, 2, 2, 2, 2, 3. And this, let's add it up. 5, 7, 9, 11, 13, 15, 17, 19, 22. So the skeletal structure is going to be very useful. So let's just go all the way back to the beginning and let's just recap everything we've talked about. So in the beginning, there was the word, and the word was carbon, and carbon had 4 valence electrons. And the way we know, and the way we kind of organize these are atomic numbers. And atomic numbers are the number of protons in the nucleus. The atomic mass, you come from protons and neutrons. And then we got the atomic weight is the average of all the isotopes. And an isotope is just a molecule with a different atomic mass than the one that is the most dominant. And then we have these positive nucleuses, and they're surrounded by electrons, and the way these electrons organize themselves are into orbitals, and these orbitals, we describe them as SPDF. S can have 2 electrons, P can have 6, D can have 10, and F can have 14. And then the way that we kind of visualize, so we know that these orbitals go around the atom, and the way that we kind of use numbers to organize these orbitals are in the ground state electron configuration. And there we go, 1s, 2s, 2p, 3s, 3p, 4s, so on and so forth. This is a very good trick. You can just, if you draw it like this, you can just go through, and that's the direction. It kind of gets confusing because, the 3p orbital comes before the 4s orbital. All right, no, that's not the, sorry. The 3d orbital comes before 4. That's just because there's more energy here in the 3D than there is in the 4P. So now we have these orbitals that we're organizing in a ground state electron configurations, and now we have these chemicals, and we want them to bond because we know that these electrons want to go somewhere and they want to bond, and they bond by sharing. And there's different ways, like chlorine, the halogens, they take electrons, sodium, the alkali metals, they give electrons, but then carbon, the one we're interested in, it shares its electrons. It forms 4 bonds. They're all covalent bonds. And then we moved on. Okay, so now we know that these molecules are made from these atoms, and we want to visualize these atoms. So let's visualize methane. And the way methane in the Lewis structure is each individual electrons is shown. And that takes too long, so let's do the line bond. So now instead of doing 2 dots, we just do a line. And this is just showing how we can organize all these electron orbitals. And now we want to talk about there's these lone pairs because not everything's bonded. So we have the lone pairs there. and those affect the geometry, and that affects the hybridization. So now we have to describe the valence bond theory, and all this is saying is that these orbitals, right, these orbitals with these electrons, they come into contact with each other, they overlap, and they form bonds. When hydrogen forms a bond with other hydrogen, it becomes a lower energy. Everything goes from high energy to low energy. So now these two hydrogen, they form a bond. Their two orbitals meet, they bond, they become H2. Same thing here. We can kind of depict carbon has its cloud, and then hydrogen. These bonds overlap, and this is the valence theory of bonding. And in here, we got our electrons somewhere in there. And now we got to talk about the hybridization. So because, let's go back to our ground state electron configuration. There's, if we go back, we know that for carbon, specifically SPDF, there's a 2s and the 2p, and the p's can hold 6 electrons, and we have that into 4 or into 3 different different orbitals, or different kind of just holders for the electrons. And these hybrids, the way they form is that if a carbon is bonded, is based off the bond angle, but it's also a good way to kind of just rule of thumb. It's based on how many atoms it's bonded to. So if it's bonded to 4 atoms, 4 separate atoms, it has sp3 hybridization, and all that's saying is that the s orbital and then all 3 of the p orbitals are full. Ethylene, it has an sp2 rule of thumb. It's bonded to 3 separate atoms, 2 hydrogens and 1 oxygen. It has an sp2 hybridization based on its bond angle. And then if a carbon is only bonded to 1 other or 2 other atoms, 2 atoms in total, it's a sp bond angle, and it will have 2 pi bonds. And this is kind of the cheat sheet that I like to use, and this is what I use on tests and stuff, and that helps me a lot. And now we kind of talked about this. It kind of goes back to the molecular orbital theory, and this is just a way to visualize it, but it's not as helpful, at least not right now. And lastly, so now we know that these carbons have valence electrons and they like to bond, and we want to visualize these bonds, and we want to know a little bit about them, and now that we want to draw them. And the way we draw them is in skeletal structures. So now we can kind of combine everything. So let's talk about hybridization. So what do you think the hybridization of this carbon is? sp3. You got the 3 hydrogens out here, 3 hydrogens. And because in these skeletal structures, go back to the rules, carbon atoms are not shown. They're shown as lines. So we got their lines. The hydrogens are not shown. We just assume. So we assume that there's all these hydrogens. There's as many hydrogens as we can fit. And then atoms other than carbon are shown. Oh, not nitrogen. I'm sorry. Hydrogen. So let's talk about sp3. So we got 3 hydrogen. This is going to be sp3 right here. We have 2 oxygen, or 2 hydrogen. So there's going to be sp2. And this, you guys, right here is going to be sp3. Or, no, sp3. Yeah. So yeah, that is kind of, that is the synopsis of chapter 1. So yeah, it's sp3 because it's bonded to 4 separate atoms. So yeah, they're all sp3, sp3, sp3. So in like butane, for instance, sp3, 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 sp3. They're all sp3. But if we added let's say we added a double bond here, sp2, sp2. So yeah. So I hope this helped. This is, like, again, specifically for Chem 361. Sweet.